The next figure we look at is the one defined as follows. And we're going to do a numerical example first. We have negative 3, 0, and 3, 0, 2 points lying along the x-axis at equal distances from the origin. We could do the same for any 2 points, but we're going to use 2 points that lie on the x-axis at equal distances from the origin because the algebra is much simpler in this case. And we have a point x, y out here. Now, whatever this point is, it lies at some distance which we'll call d1 from negative 3, 0, and another distance which we'll call d2 from 3, 0. The condition we want is that the sum of these two distances is always 7. d1 plus d2 equals 7. There are a lot of different ways to make the distance 7. We could have distance 3.5 this way and 3.5 this way. We could have a distance of 6 this way and 1 this way. There are an infinite number of combinations of distances that will give us this sum. So there are an infinite number of points that could satisfy this condition. Now, the first distance, if we draw the fundamental triangle here, the sides are going to be x minus negative 3 and y minus 0 from this point to this point. And from here to here it's x minus 3 and y minus 0. And we're going to square those, put them under the square root and so forth. The usual thing that we do with that fundamental triangle. So we have expressions for distance d1 and d2. Now, the condition that d1 plus d2 be 7 is then expressed by this equation. This is the distance from the point negative 3, 0 to xy, and this is the distance from 3, 0 to xy, as you can easily verify. So this has to equal 7. Now we get into some fairly messy algebra here, so be prepared. What we want to do is something similar to what we did before, where we got that nice equation of a straight line between 2 points. In the previous example, where we've got the points that were equidistant from 2 points. But now we want the sum of the distances from 2 points to be the same, and it's going to be a little more complicated. So as I say, be ready for some messy algebra. Okay, we have square roots here, and we want to get rid of them because they're kind of in the way, so we square both sides. The only catch is, when we square both sides, we're squaring an a plus b. When we square a plus b, we get a squared plus 2ab plus b squared. That is the square of this plus the square of this plus 2 times this times this. And that's what we write down here. Now I haven't filled in all the stuff underneath the square roots, but it's understood that this is a square root here, and what's under this square root is what's here. So we have this equation. Of course, what we have right here is the square of this square root. What we have here is the square of this square root. What we have here is the square of 7. Now that doesn't seem to be any progress. We had square roots here, and we squared to get rid of them. We still got square roots. The difference is that we had a sum of 2 square roots here. So we had square roots in 2 different terms, so that when we squared both sides, we ended up with this cross product term here. In this case, we have the square roots all in one term. And here's the term. So it turns out that we're going to be able to get rid of the square roots if we just do the right thing and square both sides again. The right thing consists of leaving these square roots on the left-hand side. Now I've written them out here. It's 2 times 2 square root. Well, I've written what's under the square roots here this time. I haven't used ellipses as dots. And then I take all these other terms and subtract them from both sides, get them over here where they're out of the way. So now I have 2 times the product of these square roots equal to this. Now this expression, when we square the x's and so forth and simplify, it becomes a little bit simpler. It's only a trinomial, so it's nothing to get too excited about. Now here at the top I've written the same expression again. Now I'm going to square both sides. Squaring both sides of this expression, the left-hand side comes out pretty easy. it's just going to be 2 squared, which is 4, and then the square of the square root is just the quantity, and the square of the square root is just this quantity. And then we have to square the trinomial. And we square the trinomial by repeated application of the distributive law. In other words, we write down this times itself and then use the distributive law intelligently. Remember, as I've said, FOIL doesn't help you here because it's not two binomials. You have to know how to multiply using the distributive law. We've been over that in earlier parts of the first semester. So anyhow, I'm not going to belabor the point here. We multiply this trinomial by itself, and this is what we get. Okay, well, you know, that's kind of nasty. Could be worse, but it's pretty bad. And it's going to get even a little bit worse because we have to multiply the left-hand side out. The right-hand side now consists of just nice terms, y to the fourth and x to the fourth and x squared, y squared, and all that stuff. But on the left-hand side, we're going to get a lot of stuff. Again, we have to use the distributive law to multiply these things out. And it turns out that we get something like this. And that's equal to dot, dot, dot. Here just stands for the right-hand side. I didn't have a lot of room. Didn't write it out again. And I'm going to do the same in the next step. I'm just working on the left-hand side right now. So if I multiply all this out and simplify it, I end up with this stuff. Of course, that's multiplied by 4, so I go ahead and multiply through by 4, and I get this. Okay? Now, I've got this equal to this. I've written out the right-hand side now, and I've got really a pretty messy situation, somewhat under control. Okay? What I've had up here was a lot messier than what I've got down here, because down here I've just got plain old fourth order terms, y to the fourth, x squared, y squared, and lower terms, y squared, constant terms, and x squared terms. Now I note that something really nice happens. And I'll also note that this wouldn't have happened if the points weren't lying on the x-axis at equal distances from the y-axis. Okay, I've got 4y squared here and 4y squared here. I've got 8x squared y on both sides. I've got 4x squared on both sides. These are the only fourth order terms I've got, only terms of fourth degree. Okay? I've got this, this, and this. Everything else is just quadratic. Now, quadratic's bad enough, but fourth degree is really bad. And we're rid of the fourth degree. And when we simplify and put our constants on the right side and then our quadratic terms on the left side, we get this equation. And we're going to put this into what's really standard form, and we'll see why this is a standard form later. I really want a 1 on this side, and I want everything on this side to have a x squared or y squared in the numerator and something squared in the denominator. Now, in order to do that, I divide through by 637. For example, the x squared term will be 52 over 637 times x squared, of course. If I put that in the denominator, it becomes 637 over 52. And if I write it as the square root of 637 over 52 squared, I've got it in the form that I want it. And this is the form, and it turns out that this is what we call the standard form of an ellipse. And we'll go on with this next time.